Hari Om. Here we discuss moving coil galvanometer. Galvanometer, you might have heard, it's an instrument used to detect the presence of current along with its direction of flow. We will be using that in the lab for measuring the direction of flow of current, like all these things. But here we are discussing the theory behind the working of a moving coil galvanometer. Why it is called moving coil galvanometer? Because there is a coil, a rectangular coil inside this. And this coil will be twisting according to the direction of flow of current. So let us see the main parts of that moving coil galvanometer. There is a rectangular coil kept balanced on a balancing spring to the base, and it is actually hanging from the screw here, and this portion is a thin fiber made of phosphor bronze, and at the end of the phosphor bronze fiber there will be the rectangular coil cap. The other end of the coil is connected to the spring and going through. So the current can come from X and flow through this rectangular coil and find its way this way. Now to provide a magnetic field there, we have got two magnetic pole pieces, North Pole and South Pole, as shown. That is having a curved face to get a uniform field there throughout. Let us see how it is. Now, a magnetic field is acting from north to south direction, and a current is flowing through it, and thereby there will be a torque acting on it, and the coil starts rotating. Due to the rotation, from the rotation we can find out how much is the current flowing. Okay, that is the A. So, anyway, main parts are same. Now let us see the principle of the moving coil galvanometer. The principle is that whenever a current carrying rectangular loop is kept in a uniform magnetic field, it is acted upon by a torque and found to be rotating. This is the principle of working of moving coil galvanometer. Now that theory we already seen there, and I am taking the equation directly. Suppose there are n turns for the coil and the magnetic field existing, let it be B, and current I is flowing through it. Then that flowing current produces a deflecting torque on the rectangular loop, and the loop will be rotating, and it goes and stay at a particular point getting balanced. Now why it is getting balanced? Because as it starts rotating, this phosphor bronze fiber and this vertical system will be having a restoring torque produced on it, and that restoring torque is making that thing to balance at a particular point. And as it is balanced, you can see deflecting torque is equal to restoring torque. Remember, deflecting torque is produced by the current flowing through the loop, and restoring torque is developed on the suspension fiber. Now this balances at an angle of theta, then deflecting torque can be taken as N I A B cos theta, where theta is the angle through which it is twisted and balanced. Then that will be equal to C theta, I can write. Restoring torque, I can take it like this, where C is called coupled per unit twist of the suspension fiber. C is called coupled per unit twist of the suspension fiber. It's a constant for that particular fiber, or that you can get from the data chart. Okay. Now from this balancing you can arrive at NIAB cos theta equal to C theta, where the current I equal to C by NAB, C by NAB into theta by cos theta. Now this is the equation for current we are getting, and we cannot say it's a linear function because here this theta by cos theta is coming and this theta by cos theta is making a problem here. So this nonlinearity can be removed so that you can get current I directly proportional to angle of twist. Now how it can be done? That is the main part of the making of what we call moving coil galvanometer. To overcome this problem, we will be taking the windings on a winding on a solid soft iron cylinder. Solid soft iron cylinder. A cylinder made of soft iron, and on which you are making the windings. Okay, like this. So if I take the windings on solid soft iron cylinder, it comes like this. See, the cylinder will be like this, and you cannot see this part here. Okay, it appears like this. Cylindrical portion, and on which the windings comes. Now, what will happen? That earlier the magnetic field lines were moving straight from north to south. Now what happens is, introducing that soft iron cylinder, the magnetic field lines are formed to bend as it enters into the solid soft iron cylinder. That we can see here separately. See, the magnetic field when it enters into the solid soft iron cylinder, suppose I view it from top. This is the north pole and this is the south pole. I am looking from the top. Then the field line comes from here and goes into and okay, like this. So the magnetic fields are now going into the soft iron cylinder and coming out because of the property of the ferromagnetic. Now what happens now is, as far as the windings is concerned, you see the winding will be now coming like this. If it deflects due to the current flowing, you can see the winding also moves along this way. Whatever the orientation be, whatever the twist be, you can see the plane of the coil comes parallel to the magnetic field. See this? Okay? So part of this goes like this, and here the part comes like this, and for the rectangular loop is concerned, it is going like this. So the field direction and the plane of the coil will be always parallel to each other, and therefore, if that is parallel to each other, then theta will be 0 and NIAB cos theta becomes the maximum. Then what happens is that current I will be equal to C by NAB into theta you get. Now whatever the twist be, the deflecting torque becomes maximum for any orientation, but this theta will be there because this theta is actually the twist produced on the suspension fiber. That twist will be always there. Current flowing, the armature coil or the coil will be rotating, and due to that rotation, deflection, there will be a twist on this fiber always. But whatever the twist be, the plane of the coil and the field will come parallel to each other. Therefore, this part will be always maximum. That is what you have to understand. Okay? Now, to make the field radial like this, we are introducing the solid soft-type cylinder. Now you got the equation here, and therefore I can say I equal to G into theta, or current I directly proportional to the angle of twist. So depending on the angle, you can identify whether the current is a strong current or a weak current. And then I introduced a constant called G. That G is called capital G is equal to C by NAB, called galvanometer constant. Galvanometer constant. Okay? So these are the main points to be noted in the case of what you call moving coil galvanometer. The theory part only, practical side we have to see. Okay?